Hello everyone, Kevin with Buesing Corporation. I was involved in the pre-con process of the project, which is scoping and estimating of the project. So this project generally was a expansion of existing Banner University Medical Center. It used to be Good Samaritan. So they were implementing a new emergency department, which is the first 3 floors, and a tower foundation below that. And then they were going to build patient floors above that. So the building will be about 16 stories, or about 650,000 square feet. Essentially, the project total is about 7 different phases, which involves an APS yard, parking lots, road work, utility relocates, and as Adderson mentioned, 3 different basements. And the last slide there, the demolition of an existing garage took place right before we arrived, and they removed all the surface component of that garage and left the below-grade caissons for us to remove during our earthwork. Project description, essentially 3 different shoring phases which relate to the below-ground structures. So phase 1 included a solenoid shoring and tensioned solenoid system. Just very quickly, you don't know what a tension solenoid is. It's passive. Typical solenoid is passive, and a pre-tensioned or slight torque in the field is a pre-tensioned solenoid. Phase 2 included a solenoid shoring and tension solenoid system as well. And then phase 3 was a hybrid of shoring and underpinning for right adjacent to the existing tower, which you saw in one of the pictures. And you can see the 3 blue areas there, and a lot of the work happened to the south of this, as well as wrapping around to the north. So pretty large expansion for this project. Phase 1 solenoid shoring system. You can see the existing tower in the background. Is kind of an iconic architecture there. It's a little bit dark. You can see the shotcrete wall there with the soil nails, and this is actually an expansion of an existing basement where there was a combination of wall line and off wall line type shoring. Phase 2 included this basement area, and it was a combination of off wall line and wall line shoring, regular soil nail, tension soil nail. And we were also holding up part of an existing basement, underpinning that, as well as underpinning underneath a proposed future grade beam. And then phase 3 included a hybrid shoring underpinning system for the patient tower. And I mentioned it's a 16-story tower, so as you well know, that mat foundation needed to be appreciably below grade, which meant it was going to go below the existing foundation system of the existing tower. And so that you can see the footprint there as it has the mat rebar on the bottom. Some of the project highlights. So the total construction cost for Banner Health is about $400 million. Obviously, we've discussed it includes multiple phases, multiple years. I think the tower is supposed to open in sometime in 2019. The project team that Banner Health selected, they selected HKS fairly early on with some prior experience. They brought in DPR construction through an interview process and qualification process. And then additional contracts were the excavation and shoring underpinning contractor, which they eventually selected Buesing. And then the shoring underpinning design engineer, because it's the design-build relationship between Buesing and AMEC, they are our shoring engineer on design-build scope. Up in the right-hand corner, it talks about an IPD, Integrated Project Delivery Method. For those of you that don't know what that is, you've heard some other acronyms like an Alternative Project Delivery Method, APDM. And so those are essentially alternate contracting methods to the traditional design first, go out to bid and bid process, select a contractor and go build it. So there are a variety of alternate project delivery methods. Fairly common as a CMAR, design assist, design build. So very quickly, the integrated project delivery is Banner Health wanted the best of a couple of different worlds there, where they wanted to be the lead in the design, the final decision maker on the design, and they wanted the contractor on board early enough to influence the design, provide constructability and cost estimates along the way. So instead of having a linear contract method and agreements through the architect to the contractor, or in a CMAR scenario, it would be a contractor first, architect second, and engineer below that. So this way is more of a triangle contract where it's integrated and all three kind of have equal decision power, equal commitment to deliverables, commitment to collaboration. So IPD might be the next new thing out there. As I mentioned, the shoring, as often is the case, is designed as a design build. If you guys don't know, most of the architects and structural engineers do not design the shoring system, and at best they might show a line on the drawing saying shoring required here. And it's up to a design build contractor engineer team, similar to Buesing and AMEC, to put that total solution together. So the drawings are not going to provide the detail enough to bid it accurately. So we have to collaborate enough during the bid process to be able to put a price to it and go to contract without even having the drawings telling you what to do. In that early process, we did have a BIM or Revit model, and so we did utilize the BIM model a little bit during the pre-con and estimate process, and helped us understand what some of the existing foundations were, existing utilities. It was the best information they had at the time. Obviously, these guys will talk about some of the challenges and surprises that came along the way, but certainly including a Revit model in the early phase of pre-construction is certainly important. I think this is where Bob takes over and talks about highlights on the shoring underpinning.
Hi guys, I'm Bob Pettit, also Buesing. When this project came to us, I'm the guy in our company that pores over all the drawings and figures out what do we have to build. So I started going through the drawings, structural, architectural, plumbing, civil, etc. Figure out what exactly do we need to build. And then through that we can figure out what steps do we have to make to fit it, to make the structure we have to build fit in the hole that we have, in the space that we have. Through that, we found that there were several places where we had to underpin. There were some spaces where we only had inches of space. There were some places where we had to actually put our shoring system, a soil wall, under an existing utility tunnel. And then we had some loads, 330 kip loads that were pretty close to our shoring system. And then I get with Steve here and Addison, and I say, okay, so Steve, we have this much space. Steve has a lot of experience in actually building the work. And we say, okay, we have 4 inches of space, we have 330 kips. What kind of stuff can we come up with to hold this up? And we start spitballing ideas. Addison has a picture right here. What one of these might look like. This we were talking about one the other day. Right? So this is not Addison's kid playing with this paper last night. This is us kicking ideas around a few days ago about a different project.
Well, that I think just complement what Bob's saying. I mean, the big challenge on that was spacing. I mean, you got a really tight space, so they could not put like big equipment there to drill beams. And the fact that it was too close to a 2-floor garage make it harder for them to put the big equipment there. You gotta be like a small kind of solution. And again, he said, oh, well, we got column loads of 330 kips to be hauled, and we didn't have access to the 4 points of the spread footing there. We had access to half of the spread footing. So we kick around a bunch of conversation. That was during the bid phase, and after that, say how are you gonna underpine that. You cannot put soldier beam piles. You got a limit amount, and we decide, hey, maybe we gotta go and do a solution with a micropile. Well, now there was a second problem in terms of the micropile. We couldn't put on the micropile only. We had to have a case in the beginning, and that was my first call, saying, well, you're gonna have to have a case. You're gonna have a moment there, and the micropile itself is not gonna handle it. And we kick around, talk about back and forth about how you use that. The case, it wouldn't work because we didn't have enough space in the footing to put the case without having to construct something else in there to connect to the column footings and other footings in the place. And then this would impact the shoring, because the shoring, that's how we enter the so for you that don't know, offline and online shoring means, when these guys use online shoring, means they using the shoring to pour the new structure. So that structure has to be inches within the alignment, so that the structure will come with that mat foundation and that walls and get the dimensions they need on that plans. Well, and that make another challenge in terms of the solution for the process. So talking back and forth, we come up with a solution of put the micropiles, but adding some anchors and nails in there to hold the moment in there. Well, the micropiles would have to be, these would still have to be excavated. So the micropiles would have to handle some portion of the load during a initial excavation of at least 5 feet, and to get the first row of anchor, or in some locations where like just soil nails, but in locations where we have the underpine, we had to use the anchors to keep the movement down. So you guys wanna talk a little bit about these pictures, the problems that you guys find there?
The picture on the right, what happened is in the field when we got to construction, this footing was what is it, this one? This footing right here was actually bigger in the field than it was on the drawings. So we had a system designed for that area, and it wouldn't work. We either would have had to saw cut that footing off, which can the wall stand with the footing being smaller, and then build some kind of a grade beam and tie into it that way, or we came up with this harebrained idea called core through it, scarify the inside of the hole, and then Adderson, as you might expect, he doesn't like to do anything until he checks to see if it works. So we like to say, hey, we'll do this, and Adderson, oh no, we got to check. So he checked, and we wound up proving that the concept works by what's that?
Load test.
Yeah.
Right.
So we cored a hole through, we put our micropile in it, we scarified the inside of it first. We put our micropile inside of it, let it cure, and then I think there's a picture of the load test.
Yeah, I'm gonna have later. But the big concern with that was the connection. We are designed for high loads, and we are worried about not having enough punch shear capacity in that existing footing to hold the loads that we designed for. So, and the micropiles is a high strength micropile that's just 3 inches in diameter. So it was a small element in there and had to get some moment there. So we were concerned about punch shear, concerned about the buckling and things like that. And they say, all right, we can try to do that because it would be just a friction connection between the existing and the new ground. But if you do that, I want to load test that to see if your connection is going to handle the load. And we did, they were creative with that, you should patent that. Did a tool to scarify the hole, so provide some better friction between the existing and the new ground there. and worked just fine. We did it. The capacity was way beyond what we designed for. This is kind of the design, a little bit of the design sections. We gave two options to them in terms of micropile types. It's just hollow core bars, self-drilling. So they have a soil type that requires some self-drilling, so they don't have to casing. That was another challenge for the project. How you're gonna do that without causing a lot of troubles? If you have to case in the hole and do all that aspect, the money that you would save would be gone. They save some money with the solutions that we present, and they can talk about the savings. So it was a hollow core bar. They can drill a hollow core bar. Basically, they drill the micropiles. For some of you that don't know, they drill the micropile and the grout at the same time, and that's make your hole stable for areas where you may have caving soils and things like that. So the tieback that we used was R38N, as well was a hollow core bar, self-drilling bar. There was driven and post tension aftermath, and there is a soil layer. The soil layer, we keep the bar the same. We could decrease the size, but it just because it would make easier for them, use a standard bar, we kept all the same values. This is one of the sections that was designed with the anchor. Here you can see it is the micropile. All right, obviously on top you got several different footings. You got I think we had 2 columns in one wall, the north wall, the east wall. We had a spread footing, but a continuous footing that was about, I think, 7 kips per foot, something like that. And the other wall had these 2 330 kips and 2 70 kips loads each side of the wall. We designed a face for 400 PSI concrete. That 500 was a requirement during construction of one of the walls, the east wall. They had to cut the footing, and we didn't have space to make the connection with the micropile because the footing now is too short. It's too close to the stem of the retaining wall that was holding the 2 garage. And when they cut that, we had to create a reinforced concrete beam and connect that so we could put the micropiles in there. We're gonna talk a little bit more about that, but that micropiles was better because we didn't have, again, space. And there was a series of interactions, and you can talk a little bit about
Let's
that.
do right now that.
Yeah,
So, you know, we read the plans and we know what we need to do, and there was a sewer and a water line that were to be relocated. Maybe we don't know the whole concept. We're just the dirt guys, right, and the drillers. So we begin digging and we see these lines here and we say, well, those need to be relocated. Remember, our micropiles are inches away from an existing basement floor into the footing, and now we have a sewer and a water that are, 8 inches or 8 feet above where the footing is. So then that turned everything. Oh, I thought you were getting there. That meant that we had to batter everything and get it in where it needed to go. And so just because sequence wasn't right, we had to come back to the drawing board again and say, okay, that was a great idea, but now we need to batter the piles. So what on earth are we going to do now? What effect does that leave us with for the rest of this work? And that was just a small 40-foot section of this. Maybe it was a third of the whole job for how small it was, but it's all right. Let's create again. Let's try to figure out what we're going to do next.
Yeah, this is just one of the sections. This is small footprints excavation. We had like about at least 5 different sections. It was 5 different solutions, and it was, what is each wall, like 150, 200 feet?
Not
even that.
80
So
feet.
it's very small, but very challenging in that aspect. And
One thing you can't see in any of these pictures is that on the north side we had an existing building, on the west side we had an existing building, on the east side we had an existing building, and on the south side we had a utility tunnel with a sewer manhole sitting on top of it. So we had to figure out how to get all the dirt out of the hole, all the equipment into the hole, and build all the tunnel without breaking the utility tunnel, the sewer manhole.
The utility tunnel that had an unreinforced floor because no one would ever need to reinforce it, right? So, you know, there's just a lot of things. Wasn't in the right place and the hole got smaller. It was all those.
There's a lot of moving
factors.
parts. I mean, these are, again, it's just a section. That's what we did to kind of hold that and have a point of support of that micropiles to hold in terms of buckling. You got to put in there, put some tension there, not enough to compromise that. Yeah, this is the loads that everybody's talking about. This is the footings, 2 columns. I think you got a picture that I could just pass on that. You can explain that. That's why they talk about tunnels and.
Yeah, so we're gonna, I can't see this. Okay, so this over here is the curved wall, which would be on the east side.
From beneath, right?
Yeah, this we're under the building looking up at what we're building here. So this is the curved wall where we had to put a section of that had the batter piles in it, and then over here existing building, over here existing building. This right here is the 330 kip load footing. That one's 270 kips, and then this right here is the 100 kips per linear foot on the wall footing. And then back here is the utility tunnel with the sewer manhole on it. On the that would be on the south side. So this is, I mean, you can see, and then what you can't see is that this building over here is now 10 stories tall by the time we get there. The building that's right here is, those footings are for that iconic architecture that Kevin referred to earlier. I mean, so really the only way we could get anything in or out of here was on the south side, and we had to figure out how to cross that unreinforced utility tunnel, which is that guy right there.
On that, just to clarify, this you're looking north from above here. That's a wall that has the big footings. There is another column footing you cannot see in there. And these 2 tunnels and the wall that was cutting. You guys gonna see some pictures there, so I'll give you a better, just to give an overall view of a lot of things that happen. So you got utilities here, utilities going on here too. I mean, there is some design modifications that we thought there was a great beam underneath the tunnel, so we could do just soil nail. And then that we went, visit the site, they changed the design, put just a steel beams between 2 drill shafts they installed here. So the tunnel would have to be probably short, and we had to get the structural plans and start to looking at that and see that would hold some because these walls are inside the tunnel. You guys gonna see the picture. How many feet was inside? Like 3 feet?
Yeah.
About 3 feet inside to give space to the mat foundation here. And we had to see if that would hold. It's kind of the overall picture of the loads. It's hard to see here, but there is the loads here. It's just the 2 footings here. You can see these 2 footings. There is a continuous footing here. That's the wall in the east side that was cut, and we had to do some connection to be able to put down the pine. They would work, the shoring guys and the structural guys that do the mat foundation or the labor would work below this wall here. That's the SAPS tunnel, and this here is the utility tunnel. The utility tunnel was just a spread footing, just a regular spread footing with a slab, non-reinforced slab on grade. So we had to create a new system to that, mainly because of the movement. You got utilities they use in the hospital. I'm gonna pass here. This guy's gonna explain a little bit about the construction. I'm sorry for the picture. It's a little hard to see. It's better on the computer.
Yeah, so this is what I was kind of talking about earlier. So this is the south side. This is from the north looking south. And you can see existing building over here, existing building over here. There's an existing building behind us. And then this is how we had to get all the dirt, all the materials in and out, everything. So we used this long reach excavator. And that was really our elevator. We brought everything down and up with that. We had to use cranes to get the equipment in and out. And This is some more pictures. This is the
East wall.
yeah, this is the east wall, and this is that sewer and storm drain we were talking about that was relocated above us that we had to put these batter piles in. This is the guys. Come on, Steve. This is your
Yeah.
But this is the guys putting in the micro piles through that footing that we cored through. Unless Steve talk more about building.
Well, anyways, you know, I'm not gonna hit the right button here, but in the end, these are the things that we saw that even on paper that we poured through, you know, those utilities were going to be relocated, but it wasn't until after the structural, you know, because those are active sewers into the hospital. So, well, we have to build that to get this, and initially we didn't know the whole sequence of the whole project. So those are just things that we find, and it's good to have a team or a partner who we can pick the phone up, you know, our grease-covered gloves, and say, hey, we got a problem. Do you want pictures, or do you want to see it with your own eyes? You know what I mean? And let's see what we can do. Or do you want just chicken scratches on a napkin? And maybe some of them want all three, and that's fine too. But in the end, it was, you'll see the bar. It's 73 millimeters, so it's a heavy wall hollow core or hollow self-grouting bar. Some people will call it self-drilling, and it doesn't really drill itself, but certainly it grouts itself. But and all that flushing and grouting, you know, we're talking about a basement that was 20 foot deep. That was maybe 2 of these rooms, and we had, I think, 7 different systems of shoring.
Yeah.
You know, as you just kind of make this 360-degree panel around this thing, this is different, this material's different, this is waiting on this grade beam that we need to build, tie in place, and shoot, whatever. So it was a lot of fun. And congested, you know, excavator, mini excavator, drill, grout plant, all that stuff. Well, the grout plant was up top, but nonetheless, that's that picture on the one side shows how tight it was, and you know, again, you can see
It's
the
hard to see.
pictures are a little bit hard to see, but
Because the micropiles on the north side.
and what on earth? Okay,
It's the south
All right.
wall.
Oh, this, just go back here a little bit. One thing though I want to talk about this is we use that a lot just to check the conflicts and things that we had. The 3D model was very accurate, and we could, all right, now we have a doubt of how that works. Let's go then visit the site and see if that's the proper solution for that. And we have like 2 or 3 visits there, right?
Yeah.
That we went through the tunnels, we went through the back, make sure that they had all on the back of these walls, they have SEVS tunnels with tons of utilities. They couldn't put anything there. Even a hand drill equipment couldn't go inside. So crowded it was. So the solution, the traditional solution, I'll put like maybe 4 micropiles and hold that column wouldn't work. And again, we had to just work with one side. This wall here is the east wall, is what you see right here in this picture. And as Steve was saying, we didn't know about this. We thought that it would be relocated. Well, we were told that it was relocated. And when we got there, well, yeah, we had a pipe there. It's not going to be relocated. Now what are we going to do? We are already working at the limit of the buckling in micropile on a pine there. And then you have to better at 10 degrees. Well, that's make a difference in that. So the initial design that we had wouldn't work for all the areas of the wall. What we did, first of all, they had to cut short the pipe. You can see that we don't have space here to put the micropiles there. First of all, the machine would have enough space to get close to that wall. And second, even if you have that enough space, you couldn't put a micropile here. There is not enough confinement on the head. So we had to create a connection beam, connect there, and even with this connection beam, because we had a limited amount of space to work, because the mat foundation dimensions we had to better that 10 degrees because the pipe is above us here. Well, when better that in certain locations where the wall gets a little taller, we had problems in overcome buckling with this kind of micropiles without casing. So what we did a frame sort of system, and we add some anchors on top. So that anchors alleviate a little bit on the buckling side when the system work together and make the design work. So that was the only kind of solution. These guys say, "Oh, you do have to do that." I say, "Well, yes. Otherwise, you're going to have bucklings. I'm not going to have my minimum factors of safety that I need, etc., etc." But at the end, it just worked fine, right?
Yeah, we wound up on that wall. We had to talk to the structural engineer for the project, and we convinced him that he could give us 8 inches of space and make the mat footing a little bit smaller. We said, okay, look, we know that it's not your rebar mat, but we do have giant micropiles on, I think they're 3-foot centers. You know, we have a shotcrete wall, we have reinforcement in the shotcrete wall, and that's, okay, it's temporary, but it's not going anywhere, and we're using shotcrete with a 0.45 water cement ratio, so we're going to have encapsulation and we should have good corrosion protection on it. So we talked to him, and he was like, okay, fine, you can have, what did he give us, 8 inches?
Yeah.
He
can give us 8 inches.
I think he gave enough space so we could do the system, because otherwise we'd be inches out of compliance with that dimensions. Right. And that's the reason that you can see in the other picture that the 5,000 psi, because the mat was a 5,000 psi. So the only requirement said, all right, I give you this 80 inches more, but you guys gonna have to put a 5,000 psi concrete there to match with my mat foundation system. And I said that's fine, that works for us. So this is the footing sort of connection detail. You got some shear connection here. You got the micropiles, and it's not in the same plane, it's offset, but you got the anchors in there. And here you have or a soil nail, or you have anchors, depends on the location there. I talk a little bit about that?
Well, this picture, which one's the laser? Oh, cool. This is demonstrating that pull-out test we talked about, where we roughened the cord hole, and we just put a piece of bar down to essentially the bottom of footing. This wasn't a drilled bar, this was a test, and we lifted up against it to prove that basically that it's just a skin friction connection between non-shrink grout and existing concrete. And you know, you never really know what existing concrete is anyway, so that was just to prove that. Again, while, you know, curing and everything else, we're doing something else, but there was about 7 little miniature jobs all at the same time in this little hole, and that speaks to that. Again, subgrade is never the same. You'll see it dips here, so that would change some of the geometry and the loading on this section here versus this here. Again, just a lot of.
Show one thing here. That's it. So one thing that you can see as well on the construction side there, you see these little berms here. We had potential for caving soils here, so that was one of the concerns under the footing. So we proposed together with the Buesing and just do the drilling through the berms, so we control that in the case that we have. Some of these locations we find cemented SGC, or most of them.
Yeah.
And I think there is a better picture. Oh, this is, all right, this is the tunnel wall. This is the spread footing for the utility tunnels in the south portion of the site. Again, we had to better the face of the wall because the spacing, you had these concrete walls going up, and they need the space to get there. And that was one of the bottom sections. Well, if you can excavate with this negative better, and because in that area we had some cemented soil,
Cemented soil is short-lived, and in this case, he could give us some of the mat footing on the east side, but he couldn't let us infringe on the mat footing on the south side. There was a big column load that he had on the south side, so he needed all of the size of the mat footing there. So part of that on the south side was to not infringe upon the mat footing with our shoring system.
But because this was unreinforced and also the tunnel would get any moment here, we had to do again another system connection and an anchor to decrease movement and to hold that, and we have soil nails down to hold the remaining of the excavation. Here you can see that's the tunnel. They drilling here. You can talk that.
You can see the sewer line on top of it. So there's the sewer manhole right there. So sewage is coming down here into the manhole over there. And then here's the storm drain on top. This is the south wall. I think that.
That's
right
the
there.
tunnel still.
Yeah, that's the sewer manhole. That's about, and our excavator is sitting about 6 or 8 feet above that.
That's it's hard to
Yeah,
see. That's
this
the
is the
other
west-
tunnel
this is
in
the
the
west
west portion.
Yeah, so on the east side of the building to the west, butted up against that building was this other utility tunnel. And then here's what it looked like after we were done and the mat foundation rebar was in. Just a thing.
In this tunnel, you can see, it's hard to see, but you can see this kind of void here. The wall was back into the tunnel like 3 feet or so. So that's when you say, well, can this tunnel handle be hanging just this load in there? And we get the conclusion that it could handle. And so we just put the regular soil nail there. So what you see here is just regular passive soil nail underneath that tunnel, just to hold the dirt below. Final, this is the project done. After a lot of back and forth, you start.
Yeah, so through this project, we learned a lot. We learned, so one, it was one of the first projects we ever really used BIM on. If you haven't used it, I'm sure you will at some point. It's an awesome tool. We used Revit and Navisworks for the utilities on the south side. But there are some things that aren't in the model, like the utilities that were hung on the wall that, even when we did our site visit during design, after the area was open, those utilities weren't on the wall while we were designing. So that happened in a matter of a week between when we did our site visit before we went to work and when we came back to go to work. They hung those utilities on the wall. So that's some of the stuff that we, and that's where understanding the phasing of everything. So this project's very complex. So wrapping your mind around what's going to be here for real when we show up. It says it's going to be relocated when, that kind of thing. Some of the testing that we had to do.
Yeah, I think in my view, one of the things that make a lot of difference was we have several interactions. Literally, all was Buesing's office or AMEC office that we said, okay, let's brainstorm. What are we gonna do? What is the equipment that you guys have? How many inches you have from here? What I can save? What I cannot? And we literally were at fight for inches in terms of making that work, and you can see that we had to go back to the structural. The structural team and the DPR team was phenomenal too, because we could go there and say, hey guys, we cannot physically put this shoring here. You cannot have access in the back. You have a limited space here. You gotta give us something, and they understand that. The structural guys, Bob said, understand and say, all right, willing to work with us, let's do that. That's what we can do. And flexibility, that's the other thing. They were flexible enough to change the design during construction, was very hard, and we were flexible enough to accommodate their needs. Like, hey, yeah, you got the utilities now, we got a better wall. That's change the design. It's gonna change a lot. And so I probably redesigned 3 times some of that section, just because that kind of thing show up. Oh, the space is no longer that. Let's change. Oh, you need to put better, and things that. But the interaction that we have during the process, before and during the process, I think was the big lesson learned. I think.
Sure.
Yeah.
On that.
The project didn't take any longer than we had estimated, and we didn't have any change orders that we sent up the line. We had enough foresight to know that it was going to be a mess, so that was a good thing. But in the end, it was done on time, on budget, and that was because of the collaboration. And if it wasn't foresight, it was, okay, what was our good plan? Well, that's no good. We need a better plan, and we just keep going like that, almost on a daily basis.
And save money for your clients, right?
Sure.